For this portion of our conversation about human-computer interaction, we're going to talk about some established principles that we've uncovered after decades of designing user interfaces. We want to understand the fundamental building blocks of HCI. Then separately, we'll talk about how to build on those foundations to do new research and new development. To get started though, let's first define some of the overarching ideas of design principles. In this lesson, we're going to talk about the way we focus on users and tasks in HCI, not on tools and interfaces on their own. We're going to talk about the role of the interface and how it mediates between the user and the task. We're going to discuss different views on the user's role in this system. And we're going to talk about user experience more generally and how it exists at several different levels. Along the way, we'll tackle some design challenges, reflect on our own experiences, and try to apply what we learn to the broader field of HCI. At the heart of human-computer interaction is the idea that users use interfaces to accomplish some task. In general, that interface wouldn't actually have to be technological. This cycle exists for things like using pencils to write things or using a steering wheel to drive a car. But in HCI, we're going to focus on interfaces that are in some way computational or computerized. What's most important here, though, is our focus on the interaction between the user and the task through the interface, not just the interaction between the user and the interface itself. We're designing interfaces, sure, but to design a good interface, we need to understand both the user's goals and the task they're trying to accomplish. Understanding the task is really important. One of the mistakes many novice designers make is jumping too quickly to the interface without understanding the task. For example, think about designing a new thermostat. If you focus on the interface, the thermostat itself, you're going to focus on things like the placement of the buttons or the layout of the screen, on whether or not the user can actually read what's there, and things like that. And those are all important questions. But the task is controlling the temperature in an area. When you think about the task, rather than just the interface, you think of things like Nest, which is a device that tries to learn from its user and act autonomously. That's more than just an interface for controlling whether the heat or the air conditioning is on. That's an interface for controlling the temperature in your house. By focusing on the task instead of just the interface, we can come up with more revolutionary designs like the Nest, rather than just iterative improvements to the same thermostats we've been using for years. Let's try identifying a task real quick. We're going to watch a short clip of Morgan, watch what she does, and try to identify what task she's performing. What was the task in that clip? If you said she's swiping her credit card, you're thinking a little too narrowly. Swiping her credit card is just how she accomplishes her task. We're interested in something more like she's completing a purchase, she's purchasing an item, she's exchanging goods. Those all put more emphasis on the actual task she's accomplishing, and let us think more generally about how we can make that interface even better. Here are 5 quick tips for identifying a user task. Number 1. Watch real users. Instead of just speculating or brainstorming, get out there and watch real users performing in the area in which you're interested. Number 2. Talk to them. You don't have to just watch them. Recruit some participants to come perform the task and talk their way through it. Find out what they're thinking, what their goals are, what their motives are. Number 3. Start small. Start by looking at the individual little interactions. It's tempting to come in believing you already understand the task, but if you do, you'll interpret everything you see in terms of what you already believe. Instead, start by looking at the smallest operators the user performs. Number 4. Abstract up. Working from those small observations, try to abstract up to an understanding of the task that they're trying to complete. Keep asking why they're performing these actions until you get beyond the scope of your design. For example, what is Morgan doing? Swiping a credit card. Why? To make a purchase. Why? To acquire some goods. Why? To repair her car. Somewhere in that sequence is likely the task for which we want to design. Number 5. You are not your user. Even if you yourself perform the task for which you're designing, you're not designing for you. You're designing for everyone that performs that task. So leave behind your own previous experiences and preconceived notions about it. These 5 quick tips come up a lot in the methods unit of HCI. HCI research methods are largely about understanding users, their motivations, and their tasks. So we'll talk much more about this later, but it's good to keep in mind now. The ultimate goal of design in HCI is to create interfaces that are both useful and usable. Useful means that the interface allows the user to achieve some task, but usefulness is a pretty low bar. For example, a map is useful in finding your way from one place to another, but it isn't the most usable thing in the world. You have to keep track of where you are, you have to plot your own route, and you have to do all of this while driving the car. So before GPS navigation, people would often manually write down the turns before they actually started driving somewhere that they hadn't been before. So our big concern is usability. That's where we get things like navigation apps. Notice how we have to focus on understanding the task when we're performing design. If we set out to design a better map, we probably wouldn't have ended up with a navigation app. It was through understanding the task of navigation itself that we realized we could offload a lot of the cognitive load of navigation onto the interface, closing the loop between the user and the task of navigation. Throughout this unit, I've repeatedly asked you to revisit the area of HCI you chose to keep in mind throughout our conversations. Now, take a second and try to pull all those things together. You've thought about how your chosen area applies to each of the models of the human's role, how it applies to various different design guidelines, and how it interacts with society and culture as a whole. How does moving through those different levels change the kinds of designs you have in mind? Are you building up from low-level interactions to high-level effects? Are you starting at the top with the desired outcome and working your way down to the individual operations? There are no right or wrong answers here. The important thing is reflecting on your own reasoning process. In looking at human-computer interaction, it's important that we understand the role that we expect the human to play in this overall system. Let's talk about 3 different possible types of roles the human can play: processor, predictor, and participant. First, we might think of the human as being nothing more than a sensory processor. They take input in, and they spit output out. They're kind of like another computer in the system, just one that we can't see the inside of. If we're designing with this role in mind, then our main concern is that the interface fit within known human limits. These are things like what humans can sense, what they can store in memory, and what they can physically do in the world. In this case, usability means that the interface is physically usable. The user can see all the colors, touch all the buttons, and so on. With this model, we evaluate our interfaces with quantitative experiments. That means we take numeric measurements on how quickly the user can complete some task or how quickly they might react to some incoming stimulus. Now, as you might have guessed, the processor view is not the one we'll generally take when we talk about good design. Instead, we'll probably divide our time pretty equally between the other 2 perspectives. A second way of viewing the human is to view them as a predictor. Here we care deeply about the human's knowledge, experience, expectations, and their thought process. That's why we call them the predictor. We want them to be able to predict what will happen in the world as a result of some action they take. So we want them to be able to map input to output. And that means getting inside their head, understanding what they're thinking, what they're seeing, what they're feeling when they're interacting with some task. If we're taking this perspective, then the interface must fit with what humans know. It must fit with their knowledge. It must help the user learn what they don't already know and efficiently leverage what they do already know. And toward that end, we evaluate these kind of interfaces with qualitative studies. These are often ex situ studies. We might perform task analyses to see where users are spending their time, or perform cognitive walkthroughs to understand the user's thought process throughout some task. We can see pretty clearly that this view gives us some advantages over viewing the user simply as a sensory processor, just as another computer in the system. However, here we're still focusing on one user and one task. And sometimes that's useful, but many times we want to look even more broadly than that. That's when we take the third participant view. A third view on the user is to look at the user as a participant in some environment. That means we're not just interested in what's going on inside their head, we're also interested in what's going on around them at the same time, like what other tasks or interfaces they're using, or what other people they're interacting with. We want to understand, for example, what's competing for their attention. What are their available cognitive resources? What's the importance of the task relative to everything else that's going on? So if we take this view, then our interface must fit with the context. It's not enough that the user is able to physically use the system and knows how to use the system. They must be able to actually interact with the system in the context where they need it. And because context is so important here, we evaluate it with in situ studies. We can't simply look at the user and the interface in a vacuum. We have to actually view and evaluate them in the real world, using the interface in whatever context it's most relevant. If we're evaluating a new GPS application, for example, we need to actually go out and look at it in the context of real drivers driving on real roads. The information we get from them using the app in our lab setting isn't as useful as understanding how they're going to actually use it out in the real world. These are in situ studies, which are studies of the interface and the user within the real, complete context of the task. So where did these different views of the user come from? To find that, we actually need to trace HCI back to its roots in psychology. The processor view of the user goes back to the behaviorist school of psychology. Behaviorism was the dominant school of thought in psychology throughout the late 19th century. It aimed to provide a systematic way of investigating behaviors in humans and in other animals. It was largely established by John B. Watson, who was a psychologist at Columbia University. He insisted that psychology focus only on observable behavior and not on introspection. John B. Watson himself was responsible for the Little Albert experiment that you might be familiar with. In that experiment, a little boy was conditioned to be afraid of rabbits as they were repeatedly paired with loud noises. You might be familiar with some of the other big names in behaviorism as well, such as Pavlov with his dogs and Skinner with his rats. Pavlov discovered the idea of classical conditioning, where he could condition a dog to salivate at the sound of a bell by repeatedly pairing those two stimuli together. Skinner went a step further with operant conditioning and conditioned rats to actually demonstrate a learned behavior. They would press a button to receive food. The important takeaway here is that behaviorism focuses only on observable behaviors and outcomes. It attempts to understand behavior by looking only at behavior, not at the cognition that underlies behavior, and thus it has the name behaviorism. In HCI, this means looking at what designs create the right behaviors without paying a whole lot of attention as to why. If we view the user as a processor, then our design process focuses on testing observable behaviors. The predictor view of the user goes back to the next major school of thought in psychology, Cognitivism, or cognitive psychology, or cognitive science. While behaviorism was only concerned with what we could observe, Cognitivism is concerned with what goes on inside the mind. Now this covers a lot. Things like perception, attention, memory, creativity, these all occur inside the user's mind. Cognitivism started out more as a philosophical endeavor. Philosophers like René Descartes and Immanuel Kant touched on questions like whether knowledge is inborn or developed solely by experience, whether or not people are blank slates when they're born or if they're born with some kind of innate knowledge. But it wasn't until the cognitive revolution of the 1950s that cognitivism really emerged as a foil to behaviorism. And at that time, it was such a radical departure that in many places you still see cognitive science classified as a completely different field from psychology. What's particularly interesting is that this shift came about in large part due to the work of scientists working in artificial intelligence and computer science, as well as neuroscience and linguistics and some other areas that were applicable to psychology, but weren't subsets of psychology. Some of the big names in cognitivism are the linguist Noam Chomsky, the psychologist Susan Carey, and the computer scientists John McCarthy, Marvin Minsky, Alan Newell, and Herbert Simon. Many of these might be names you're familiar with if you've read about classical AI. These are some of the biggest names in classical AI thinking. Those early efforts in classical AI were specifically trying to create computers that could think like humans. And in order to create a computer that could think like a human, we had to understand how a human thought. Now for us here in HCI, the key here is that we care about what the user is thinking. We call this the predictor model of the user because predicting is a mental process, and we want to know what the user is predicting. We ask questions like, what do they predict the outcome of that action will be? What do they predict is the right action to take? Now notice here, the user is doing the predicting, not the interface. We want to get inside the user's head and understand how they predict the interface will behave. That's the core of the predictor model. Now, while behaviorism and cognitivism are well-established schools of thought in psychology, the participant view is a little more nascent. It resembles the functionalism view of psychology, which emphasizes examining mental behaviors in the context of broader environments. And it also resembles systems psychology, which emphasizes human behavior within complex systems. But in both places, the coupling between the participant view and these schools of thought is a little less well-defined. In our work, the participant view largely comes out of original research in HCI and human factors engineering. The important thing here is that while the processor and predictor views emphasize only the interaction of some user and some interface, the participant view also looks at the interaction of both within the context of a larger system. It cares about the environment in which the user and the interface are situated. So this model views the user and the interface as participants within a larger complex cognitive system. Some of the major names in this area are Edwin Hutchins, who pioneered the idea of distributed cognition. We'll talk about him more when we talk about distributed cognition in a few lessons. Lucy Suchman also introduced the idea of situated action models, which argue that we can't disentangle behavior from the environment in which it takes place. Gabriel Salomon was an educational psychologist who focused in large part on how learning happens in the context of culturally provided tools and implements. And Bonnie Nardi introduced the complementary idea of activity theory into this general idea of analyzing a user and an interface as participants in some larger activity. So anytime you're looking beyond just the user and the interface, you're likely employing the participant view in some way. But like I said, we'll talk about this a lot more when we reach our lesson on distributed cognition. Now, this has been a super quick recap of these three major schools of thought in both psychology and in HCI. There are actually entire classes available that focus exclusively on each of these or even on subparts of each of these. So if you'd like to learn more, you should check out some of the links that we'll provide below. To better understand how we might use these three views of the user, let's see how we might apply them to a design challenge. So here we have the address entry screen on Tesla's Model S. At the top, we have the text box that the user is entering text into. Below we have some results, and at the bottom we have the keyboard that they actually use to enter their text. Let's imagine we're trying to redesign it such that the user can enter the address of their target destination more quickly so they can get on with the navigation. With the processor model, we're strictly looking at the user's observable behavior, so we might construct a controlled study where we bring participants in, give them addresses to enter and different interfaces to use, and time them on different versions. Whichever interface has the fastest times would be the interface we might want to go with. There are some benefits to using this model. One big one is that we might actually be able to use existing data for this. If we assume that every time a user brings up the search bar, they're going to input an address to navigate to, we can look back and look, how long does it usually take from opening that search bar to actually starting navigation? We might be able to do that on an absolutely massive quantity of data. Another benefit of this is it enables objective comparisons. That means we could compare this text entry screen to a voice system or some other way of inputting addresses to understand how different interfaces entirely or different modes of interaction entirely can have different efficiencies associated with them. And most importantly, those comparisons are objective. There's no real interpretation involved in saying that it takes an average of 5.2 seconds to go from entering an address to starting navigation. That's just a descriptive statistic. However, there are some pretty major drawbacks as well. When we're employing the processor model, we don't see the reason for the differences that we observe. We have no real basis to understand why one interface performs better than the other. And we also can't differentiate by expertise. Usually when we're using the processor model, we're working with expert users and we're not really worried about what they're thinking about. For novices though, it's very difficult for the processor model to understand what a novice finds confusing or misleading. And most generally, the processor model is usually good for optimization, but not for redesign. If we're making small changes like the size of buttons or the responsiveness of the screen, then it can help us compare and understand which interface is performing better. But if we're going to try a comprehensive new redesign, the processor model isn't very helpful. It might be good for evaluating that new redesign once we've created it, but it doesn't give us very much input on what we should include in that redesign. If we shift to the predictor model, then we're going to actually start asking our users for input. We could bring them in for interviews, conduct focus groups, send out surveys. We could also show them prototypes for new interfaces and have them describe their thought process while trying to interact with them. We might find some simple changes that we wouldn't have stumbled upon otherwise. For example, we might find that users find a certain icon to be misleading compared to its real meaning. We might also find some information about why users choose different interfaces at different times. For example, users might prefer the voice interface while driving, but this text interface while they're parked. So the big advantage here is that we get a more complete picture of the user's interaction with the interface. We get to ask them why they do certain things, or what they're thinking about, or why they made certain choices. Additionally, this model lets us target different levels of expertise. We can bring in novices who've never seen the interface before and say, take a look at this, what do you think you should do next? But we could also bring in experts and have them reflect on how some new interface might make it more or less efficient to accomplish what they want to accomplish. But again, there are drawbacks. One big drawback is that the analysis of this can be very expensive. We're not looking at numbers and conducting little statistical tests. We're often looking at plain text transcripts of interviews or plain text responses to surveys. Analyzing those requires a lot of human attention and a lot of effort. And even then, that analysis can be subject to biases. If the person analyzing that data has some suspicions about what they think the better interface would be, they're very likely to imbue their analysis with those biases and only focus on data that confirms what they already think was true. So we have to make sure that they control for those biases. And additionally, when we're using the predictor model, we're still usually ignoring the broader interaction context. We're usually looking at the person and the interface, but not the real authentic environment in which they usually use that interface. For this interface, that could be a problem, because we might have an interface that works very well when it has the full user attention, but is significantly harder to use when the user is, for instance, driving. For example, if we were only testing a new interface in a lab setting, we might have a feature that hides what the user has been searching for if they haven't entered any new text or made a selection in the past 5 seconds. In a lab setting, that's probably fine because our users are generally only focused on the task that we're giving them, which is entering some address into that search bar. But if they're actually out driving, they might start entering an address at one red light, have the light turn green and want to pause, and continue entering it at the next red light. If it disappears after 5 seconds, then that's not really aware of the way they're using it in the real environment. So that's where the participant model comes in. With a participant model, we view the interface and the user in the context in which they actually interact. We want to look at the user and the interface as participants in some broader activity, the broader activity of driving, not just as a user interacting with one interface. Now, the benefit of this should be pretty obvious. It evaluates the interaction in context. We can understand things like the driver is distracted, or they're going to do things in different batches as they come to different red lights. And we also capture an authentic representation of the user's level of attention. If the user is going to be distracted, for example, we'll see that when we analyze the activity in the authentic context in which it takes place. But unsurprisingly, there are also drawbacks to this approach too. Just as the predictor model suggested evaluations that were difficult to analyze, the participant model emphasizes evaluations that can actually be difficult to perform. To evaluate this interface in the authentic context in which it's used, we need to actually go right along with participants. And that's a lot harder to do than just sending out a survey or bringing people into our controlled lab environment. And it also means we need to have real, functional interfaces. We can't have a person driving a car and keep holding up some prototype next to them while they're actually trying to drive. We need these interfaces to actually be designed and implemented to work in that real context. So it's hard to use this model when we're just getting started with a new design task. And finally, using the participant model means that we're exposing ourselves to a lot of uncontrollable variables. The more that's going on in the environment, the harder it is to zoom in and focus only on the impact of our designs. Now, hopefully you'll notice that the pros of some of these models address the cons of others. The processor model, for example, doesn't give us much insight into what novices are thinking, but the predictor model is particularly good at targeting novices. The predictor model makes it difficult to conduct real objective comparisons, but that's exactly what the processor model is good for. Neither the processor nor the predictor model take into consideration context, but that's what we get when we consider the participant model. But it doesn't isolate variables very well. It's subject to interference from things that we can't control. But the processor model is very good at isolating those variables. So the major takeaway here is that we'll likely use all these different models at different times and in different contexts. And the data we gather from one might inform what we do with another. We might start with a participant model where we just ride around with users watching what they do. Based on that, we might observe that they spend a lot of time fumbling around to return to the same few locations. So then we might redesign an interface to include some kind of bookmarking system and present it to users in interviews. There, they might tell us they like that design, but further note that they don't need a long list of bookmarks. They really only need work and home. So based on that, we might then design an interface where a simple swipe takes them to work or to home, depending on where they are right now. And in fact, that's how that Tesla navigation screen works. If you just swipe across the navigate button, it'll automatically take you to work if you're at home, or home if you're at work. And then finally, we might test it with the processor model to see just how much more efficiently that new interface allows users to put in their destination. The results of each design phase inform the next, and different phases call for different types of evaluation, which echo the different models of the user. Good design. A GPS system that warns you 20 seconds before you need to make a turn.
In 1,000 feet, turn left.
Bad design. A GPS system that warns you 2 seconds before you need to make a turn.
Turn left now. Hurry.
It sounds funny, but which view you take on the user can have a huge impact on the success of the interface. If you view the user just as a sensory processor, you might think that we only need to alert them a second before the upcoming turn, because, after all, human reaction time is less than a second. If you view the user as a predictor, you understand that they need time to slow the car down and actually make the turn, so they might need a few more seconds to execute the action of turning after being alerted that they need to turn. And if you view the user as a participant, you understand that this is happening while they're going 50 miles an hour down the road with a screaming toddler in the back seat, trying to merge with a driver on a cell phone and another one eating a cheeseburger. So it would probably be a good idea to give them a few or more reminders before the turn and plenty of time to get in the right position. Let's take a moment to reflect on when you've encountered these different views of the user in your own history of interacting with computers. Try to think of a time when a program, an app, or a device clearly treated you as each of these types of users, for better or for worse. For me, we have a system at Udacity we use to record hours for those of us that work on some contract projects. It asks us to enter the number of hours of the day we spend on each of a number of different types of work. The problem is that assumes something closely resembling the processor model. A computer can easily track how long different processes take. But for me, tracking the amount of time spent on different tasks can be basically impossible. Checking my email involves switching between 5 different tasks a minute. How am I supposed to track that? The system doesn't take into consideration a realistic view of my role in the system. Something more similar to the predictor view would be, well, the classroom you're viewing this in. Surrounding this video are a visual organization of the lesson's content, a meter measuring your progress through the video, representations of the video's transcript. These are all meant to equip you with the knowledge to predict what's coming next. This classroom takes a predictor view of the user. It offloads some of the cognitive load onto the interface, allowing you to focus on the material. For the third view, I personally would consider my alarm clock an example. I use an alarm clock app called Sleep. It monitors my sleep cycles, rings at the optimal time, and tracks my sleep patterns to make recommendations. It understands its role as part of a broader system intended to help me sleep. It goes far beyond just interactions between me and an interface. It integrates into the entire system. By my definition, user experience design is attempting to create systems that dictate how the user will experience them, preferably that the user will experience them positively. User experience in general, though, is a phenomenon that emerges out of the interactions between humans and tasks via interfaces. We might attempt to design that experience, but whether we design it or not, there is a user experience. It's kind of like the weather. There's never no weather. There's never no user experience. It might be a bad experience if we don't design it very well, but there's always some user experience going on, and it emerges as a result of the human's interactions with the task via the interface. But user experience also goes beyond this simple interaction. It touches on the emotional, personal, and more experiential elements of the relationship. We can build this by expanding our understanding of the scope of the user experience. For just a particular individual, this is based on things like the individual's age, sex, race, personal experiences, gender, expectations for the interface, and more. It goes beyond just designing an interface to help with a task. It touches on whether the individual feels like the interface was designed for them. It examines whether they're frustrated by the interface or joyous about it. Those are all parts of this user experience. We can take this further and talk about user experience at a group level. We can start to think about how interfaces lead to different user experiences among social or work groups. For example, I've known that school reunions seem to be much less important to people who've graduated within the past 15 years, and I hypothesize it's because Facebook and email have played such significant roles in keeping people in touch. It's fundamentally changed the social, the group user experience. Those effects can then scope all the way up to the societal level. Sometimes these are unintended. For example, I doubt that the creators of Twitter foresaw when they created their tool how it would play a significant role in big societal changes like the Arab Spring. Or sometimes these might be intentional. For example, it was a significant change when Facebook added new relationship statuses to its profiles to reflect things like civil unions. That simultaneously reflected something that was already changing at the societal level, but it also participated in that change and helped normalize those kinds of relationships. And that then relates back to the individual by making sure the interface is designed such that each individual feels like it's actually designed with them in mind. The options are there for them to feel like they're properly represented within the system. These are all components of the general user experience that we need to think about as we design interfaces. So keeping in mind everything we've talked about, let's design something for Morgan. Morgan walks to work. She likes to listen to audiobooks, mostly nonfiction, But she doesn't just want to listen, she wants to be able to take notes and leave bookmarks and do everything else you do when you're reading. What would designing for her look like from the perspectives of viewing her as a processor, a predictor, and a participant? How might these different designs affect the user experience as an individual, in her local group of friends, and in society as a whole if the design caught on? As a processor, we might simply look at what information is communicated to Morgan, when, and how. As a predictor, we might look instead at how the interface meshes with Morgan's needs with regard to this task, how easy it is to access, how easy the commands are to perform, and so on. As a participant, we might look at the broader interactions between this interface and Morgan's other tasks and social activities. We might look at how increased access to books changes her life in other ways. But really, this challenge is too big to address this quickly. So instead, let's return to this challenge throughout our conversations and use it as a running dialogue to explore HCI principles and methods. In this lesson, we've covered some of the basic things you need to understand before we start talking about design principles. We covered the idea that interfaces mediate between users and tasks, and the best interfaces are those that let the user spend as much time thinking about the task as possible. We covered the idea of usability and how we have to keep in mind the efficiency and user satisfaction of an interface. We covered 3 views of the user and how those different views affect how we define usability and evaluation. And we covered how the user experience does not exist just at the user level, but also at group and even societal levels. Feedback cycles are the way in which people interact with the world and then get feedback on the results of those interactions. We'll talk about the ubiquity of feedback cycles. Then we'll talk about the gulf of execution, which is the distance between a user's goals and the execution of the actions required to realize those goals. Then we'll talk about the gulf of evaluation, which is the distance between the effects of those actions and the user's understanding of those results. We'll discuss 7 questions we should ask ourselves when designing feedback cycles for users. And we'll also look at applications of these in multiple areas of our everyday lives. Feedback cycles are incredibly ubiquitous, whether or not there's a computational interface involved. Everything from reading, to driving a car, to interacting with other people could be an example of a feedback cycle in action. They're how we learn everything from how to walk, to how to solve a Rubik's Cube, to how to take the third-order partial derivative of a function. I assume I've never done that. We do something, we see the result, and we adjust what we do the next time accordingly. You may have even seen other examples of this before too. If you've taken Ashok's and my knowledge-based AI class, we talk about how agents are constantly interacting with, learning from, and affecting the world around them. That's a feedback cycle. If you've taken Rahim Bea's cyber-physical systems course, you've seen this without a human involved at all, as a system can autonomously read input and react accordingly. Under some definitions, some people would even call this artificial intelligence, specifically because it mimics what a human actually does. They act in the world, and they evaluate the result. In fact, if you look at some of the definitions of intelligence out there, you'll find that many people actually define feedback cycles as the hallmark of intelligent behavior, or they might define intelligence as abilities that must be gained through feedback cycles. Colvin's definition, for example, involves adjusting to one's environment, which means acting in it and then evaluating the results. Dearborn's definition of learning or profiting by experience is exactly this as well. You do something and experience the results and learn from it. Adaptive behavior in general can be considered an example of a feedback cycle. Behavior means acting in the world, and adapting means processing the results and changing your behavior accordingly. And most generally, Schenk's definition is clearly an ability gained through feedback cycles, getting better over time based on evaluation of the results of one's actions in the world. And Schenk's general definition, getting better over time, is clearly something that can happen as a result of participation in a feedback cycle. We find that nearly all of HCI can be interpreted in some ways as an application of feedback cycles, whether between a person and a task, a person and an interface, or systems comprised of multiple people and multiple interfaces. In our feedback cycle diagram, we have on the left some user and on the right some task or system. The user puts some input into the system through the interface, and the system communicates some output back to the user, again, through the interface. Incumbent on this are 2 general challenges: the user's interaction with the task through the interface, and the task's return to the user of the output via the interface. The first is called the gulf of execution. The gulf of execution can be defined as, how do I know what I can do? The user has some goals. How do they figure out how to make those goals a reality? How do they figure out what actions to take to make the state of the system match their goal state? This is the gulf of execution. How hard is it to do in the interface what is necessary to accomplish the user's goals? Or alternatively, what's the difference between what the user thinks they should have to do and what they actually have to do? Now, there are a number of components of this. The first component, they need to be able to identify what their goal is in the context of the system. There might be a mismatch between their own understanding and the system's structure. Think of transitioning from an old-fashioned VCR to a more modern DVR, or from a DVR to watching things on demand. The user needs to think of their goal in terms of their current system. Second, they need to be able to identify the actions necessary to accomplish their goals. Now that they know what their goal is in the context of the system, they need to identify the actions that it will take to make that goal a reality. And third, once they've identified those actions, they need to actually execute the actions within the interface. Again, imagine someone who's learning to use an on-demand video interface when they're used to using things like VCRs and DVRs. Their goal hasn't changed. They want to watch some program that's already aired. But in the context of a VCR or a DVR, their intention might be to record that program. In the context of an on-demand video interface, their intentions instead are to call up the existing version of that program. That's a mismatch between what they think their goal is and what their goal is in the context of this new system. But once they understand what the goal means in their current system, they now need to know how to pull up that program. They need to know how to navigate the menus and find the program that they want to watch and then start it playing. And then once they know what to do, they need to actually execute that series of button presses. For example, they might know what actions to perform, but they might not know where to find them. That would present a difficulty in executing those actions. So the gulf of execution takes the user from understanding their own goals, to understanding their goals in the context of the system, to understanding the actions necessary to realize those goals, to actually executing those actions. And each of these presents some difficulties. Let's take a simple example of the gulf of execution. I'm making my lunch. I have my bowl of chili in the microwave. My goal is simple. I want to heat it up. How hard is that? Well, typically when I've been cooking in the past, cooking is defined in terms of the amount of time it takes. So in the context of this system, I specify my intent as to microwave it for 1 minute. Now, what are the actions necessary to do so? I press time cook to enter the time cooking mode. I enter the time, 1 minute, and I press start. I didn't press start just now, but I would press start. I specified my intent, microwave for 1 minute. I specified my actions, pressing the right sequence of buttons, and I executed those actions. Could we make this better? There were a lot of button presses to microwave for just 1 minute. If we think that's a common behavior, we might be able to make it simpler. Instead of pressing time cook 1, 0, 0 and start, I might just press 1 and wait. Watch. So I've narrowed the gulf of execution by shrinking the number of actions required, but I may have enlarged it by making it more difficult to identify the actions required. When I look at the microwave, time cook gives me an idea of what that button does. So if I'm a novice at this, I can discover how to accomplish my goal. That's good for the gulf of execution. It's easier to look at the button and figure out what to do than to have to read a manual or anything like that and find out on your own. But once you know that all you have to do is press 1, that's much easier to execute. That's something nice about this interface. It caters to both novices and experts. There's a hard, discoverable way and a short, invisible way. But let's rewind all the way back to the goal I set up initially. My goal was to heat up my chili. I specified my intent in terms of the system as microwaving it for 1 minute. But was that the right thing to do? After 1 minute, my chili might not be hot enough. This microwave actually has an automatic reheat function that senses the food's temperature and stops when the time seems right. So the best bridge over the gulf of execution might also involve helping me reframe my intention. Instead of wanting to microwave for 1 minute, it might encourage me to reframe this as simply heating until ready and letting the microwave do the rest. Here are 5 quick tips for bridging gulfs of execution. Number 1, make functions discoverable. Imagine a user is sitting in front of your interface for the very first time. How would they know what they can do? Do they have to read the documentation, take a class? Ideally, the functions of the interface will be discoverable, meaning that they can find them clearly labeled within the interface. Number 2, let the user mess around. You want your user to poke around and discover things, so make them feel safe in doing so. Don't include any actions that can't be undone. Avoid any buttons that can irreversibly ruin their document or setup. That way the user will feel safe discovering things in your interface. Number 3, be consistent with other tools. We all want to try new things and innovate, but we can bridge gulfs of execution nicely by adopting the same standards that many other tools use. Use Ctrl-C for copy and Ctrl-V for paste. Use a diskette icon for save, even though no one actually uses floppy disks anymore. This makes it easy for users to figure out what to do in your interface. Number 4, know your user. The gulf of execution has a number of components: identifying intentions, identifying the actions to take, and taking the actions. For novice users, identifying their intentions and actions are most valuable, so making commands discoverable through things like menus is preferable. For experts, though, actually doing the action is more valuable. That's why many experts prefer the command line. Although it lacks many usability principles targeted at novices, it's very efficient. Number 5, feed forward. We've talked about feedback, which is a response to something that the user did. Feed forward is more like feedback on what the user might want to do. It helps the user predict what the result of an action will be. For example, when you pull down the Facebook news feed on your phone, it starts to show a little refresh icon. If you don't finish pulling down, it doesn't refresh. That's feed forward, information on what will happen if you keep doing what you're doing. Many of these tips are derived from some of the fundamental principles of design pioneered by people like Don Norman and Jacob Nielsen, and we'll cover them more in another lesson. The second challenge is for the task to express to the user through the interface the output of the actions that the user took. This is called the gulf of evaluation, because the user needs to evaluate the new state of the system in response to the actions they took. Like the gulf of execution, we can think of this in terms of 3 parts. There's the actual physical form of the output from the interface. What did it actually do in response? There might be something visual, there might be a sound, a vibration, some kind of output. The second is interpretation. Can the user interpret the real meaning of that output? You might think of this in terms of a smartphone. If a smartphone vibrates in your pocket, can you interpret what the meaning of that output was? Or do you have to pull the phone out and actually see? And then the third phase is evaluation. Can the user use that interpretation to evaluate whether or not their goals were accomplished? You can imagine submitting a form online. It might give you output that you interpret to mean that the form was received, but you might not be able to evaluate whether or not the form was actually accepted. Once they've received and interpreted that output, the final step is to evaluate whether or not that interpretation means that their goals were actually realized within the system. Take our on-demand video service example again. Imagine that the user has gotten all the way to finding the program that they want to watch, and they've pressed the play button on their remote. Imagine the interface responds by hiding the menus that they were using to navigate amongst the service. Can they interpret the meaning of that output? And can they evaluate whether or not that interpretation means that their goals were realized? If they're a novice user, maybe not. An expert might correctly interpret that the screen blacking out is because the service is trying to load the video. They then evaluate that interpretation and determine that their goals have been realized, that the service is trying to play the show they want to watch. But a novice user might interpret that output to mean that the service has stopped working at all, like when your computer just shuts down and the screen goes black. They then incorrectly evaluate that their goals were not actually realized in the system. We might get over this by showing some kind of buffering icon. That's a different kind of output from the system that helps the user correctly interpret that the system is still working on the actions that they put in. They then can evaluate that maybe their goals were correctly realized after all, because the system is still working to bring up their show. So as you can see, each of these 3 stages presents some unique challenges. Let's take a thermostat, for example. I have a goal to make the room warmer. So I do something to my thermostat with the intention of making the room warmer. What does the system do as a result? Well, it turns the heat on. That would be the successful result of my action. But how do I know that the heat was turned on? Well, maybe I can hear it. I might hear it click on. But that's a one-time kind of thing, and it might be quiet. And if I miss hearing it, I have no way of double-checking it. So I'm not sure if I heard it. I have to go find a vent and put my hand on it and try to feel the heat coming out. And there's more going on in a heater. It might have worked, but the heater doesn't immediately turn on for one reason or the other. These are signs of a large gulf of evaluation. Neither the sound nor the vent are optimal displays because they're either hard to reach or possible to miss. Feeling the heat might be easy to interpret, but hearing the heater turn on might not. So either way, I have to do a lot to evaluate whether or not my action was successful. And this is all for a very small piece of feedback. Ideally, if I wasn't successful, we want the system to also tell me why I wasn't successful, so I can evaluate what I did wrong and respond accordingly. There's a very large gulf of evaluation if there's no indicator on the actual thermostat. So how can we resolve that? Well, simple. We just mark on the thermostat that the heat is on. That sounds trivial, but nothing in the fundamental design of this system demanded a note like this. It's only in thinking about the system from the perspective of the user that we find that need. I can let you know as well, this system still isn't very ideal. For various reasons, it'll turn the heater on or the air conditioning off even when it hasn't reached the temperature I put in. And it gives me no indication of why. I can look at the system and evaluate that the temperature is set to lower than the current temperature in the room, but at the same time, I can see that the heater isn't on. Under those circumstances, I have no way of knowing if the heater is malfunctioning, if the switch is wrong, or I don't even know. In this case, it might just be that it's set to the wrong mode. The mode is visible, but I have to remember to check it if it appears to be malfunctioning. We can imagine an alternative message on the screen indicating the direction of the relationship or something similar that would give some sign that it's currently set incorrectly. Here are 5 quick tips for bridging gulfs of evaluation. Number 1, give feedback constantly. Don't automatically wait for whatever the user did to be processed in the system before giving feedback. Give them feedback that the input was received. Give them feedback on what input was received. Help the user understand where the system is in executing their action by giving feedback at every step of the process. Number 2, give feedback immediately. Let the user know they've been heard even when you're not ready to give them a full response yet. If they tap an icon to open an app, there should be immediate feedback just on that tap. That way, even if the app takes a while to open, the user knows that the phone recognized their input. That's why icons briefly gray out when you tap them on your phone. Number 3, match the feedback to the action. It might seem like this amount of constant immediate feedback would get annoying, and if executed poorly, it really would. Subtle actions should have subtle feedback. Significant actions should have significant feedback. Number 4, vary your feedback. It's often tempting to view our designs as existing solely on a screen, and so we want to give the feedback on the screen. But the screen is where the interaction is taking place, so visual feedback can actually get in the way. Think about how auditory or haptic feedback can be used instead of relying just on visual feedback. Number 5, leverage direct manipulation. We talk about this a lot more, but whenever possible, let the user feel like they're directly manipulating things in the system. Things like dragging stuff around or pulling something to make it larger or smaller are very intuitive actions because they feel like you're interacting directly with the content. Use that. Again, we talk far more about this in another lesson, but it's worth mentioning here as well. By loading these things into your short-term memory several times, we hope to help solidify them in your long-term memory. And that relationship is actually something we also talk about elsewhere in this unit. In Don Norman's Design of Everyday Things, he provides a different way of looking at the same information. This diagram puts a greater emphasis on what the user is doing at each of these stages. The user is setting a goal, and then planning and specifying and performing, and then perceiving and interpreting and comparing. This diagram also changes our terminology a bit, and with good reason. We see a bridge of execution and a bridge of evaluation. The reason for that is these behaviors specifically bridge the gulf between the goal and the world. They're what the user has to do to make the world match their goal, and then confirm that the world now does match their goal. Norman uses these stages to introduce 7 questions that we should ask ourselves when we're designing interfaces. First, how easily can one determine the function of the device? Or in other words, how easily can one tell that this device can accomplish that goal? Second, how easily can one tell what actions are possible to do with the device? Third, how easily can the user determine the mapping from their intent to the actual movements or actions they need to take with the device? So in planning, they're figuring out what they can do. With specifying, they're figuring out what they should do. And then finally, how easily can the user actually perform the physical movements associated with that plan? After they've done these 3 stages, something has happened in the world, and they're ready to see if they can perceive what has changed. So then we ask, how easily can the user perceive or tell what state the system is in? This is the raw information that they're getting out of the system. Then, how easily can they tell if the system is in the desired state? Or how easily can they interpret what they perceived? And then finally, how easily can the user determine the mapping from state to interpretation? Or in other words, how easily can the user compare what they interpreted as happening to what they wanted to happen? You'll notice that these match our stages from earlier. Norman also makes it even more clear by describing this specifically in terms of what the user is thinking. The user starts by thinking, what do I want to do? Then they consider what are the alternatives for accomplishing it. Then they specify what can I do to actually perform one of those alternatives. And then they ask, how do I do that? Once they've done it, they ask, what happened? What does that mean? And is that okay? I like this phrasing because it makes the distinction between interpreting and comparing a little easier. Interpreting is just about understanding what happened. Comparing involves going back to the original goal that the user had. Norman also further articulates this by breaking the process into phases that span both execution and evaluation. Closest to the world, he has the visceral phase, which is the actual physical activity or the raw perceptions. Above that, he has the behavioral layer, which is where we're actually specifying what behaviors to do or interpreting the outcome of those behaviors. And then at the top level, there's the reflective phase, which is thinking about the problem and planning our solution or comparing the results to our original goal. If we change his vocabulary a little bit, we might describe this lowest level as raw reaction, the middle level as deliberation, and the top level as metacognition, thinking about the goal, thinking about the problem-solving process, thinking about what we did and what happened. And if we rewrite these phases with this vocabulary, we start to get at a diagram you might recognize if you've taken knowledge-based AI. And if you haven't, here's a little teaser for what you'll see if you do. Good design. A phone that quietly clicks every time a letter is successfully pressed to let you know that the press has been received. Bad design. A phone that loudly shouts every letter you type.
P I C.
Remember, small actions get small feedback. The only time you might want your device to yell a confirmation at you is if you just ordered a nuclear launch or something. Let's pause for a second and reflect on the roles of goals of execution and goals of evaluation in our own lives. So try to think of a time when you've encountered a wide gulf of execution and a wide gulf of evaluation. This doesn't have to be a computer, it could be any interface. In other words, what was a time when you were interacting with an interface but couldn't think of how to accomplish what you wanted to accomplish? What was a time when you were interacting with an interface and couldn't tell if you'd accomplished what you wanted to accomplish? So it's not a coincidence that I'm filming this in my basement. This actually happened to me a few weeks ago. The circuit to our basement was tripped, which is where we keep our modem, so our internet was out. Now this is a brand new house and it was the first time we tripped a breaker, so I pulled out my flashlight and I opened the panel, and none of the labels over here clearly corresponded to the breaker I was looking for over here. I ended up trying every single one of them and still it didn't work. I shut off everything in the house. Why didn't it work? Well, in reality, there was a reset button on the outlet itself that had to be pressed. The only reason we noticed it is because my wife noticed something out of the corner of her eye turning off and on as I switched these. That was a terribly large gulf of execution. I knew what I wanted to accomplish. I could translate it into the system's terms easily, reset a breaker. But figuring out the actions to accomplish that goal was very difficult. That's a large gulf of execution. How was that?
Oh, what? Oh, sorry, I wasn't paying attention.
You weren't watching? So I have no way of knowing if that was good or not? Wasn't that a terrible gulf of evaluation? I joke, but a lack of feedback on your performance at a task, whether it be filming like I'm doing now or doing a project like you'll do later in our material, presents the same kind of poor gulf of evaluation. 15 years ago, we might not have talked about cars in the context of discussing HCI, but nowadays this is basically a computer on wheels. So let's talk a little bit about how feedback cycles apply here. Let's start with the ignition. The button to start my car is right here. Why is it located there? Before cars had push-button starts, this is where you inserted the key to turn on the ignition. Why? I have no idea. But I do know that now, the start button could be placed in any number of different locations. So why do we put it where we've always put it? Well, the reason is that's where the driver expects it to be placed. We help them across the gulf of execution by designing a system that's consistent with their expectations about how it should work. It makes it easier for them to translate their intentions into actions. Now, other times we might violate this principle because of some other benefits we hope to gain, but generally speaking, when all else is equal, we want to stay consistent with the way users expect our systems to work. So we know where the ignition button is. Let's press it. Do you think the car turned on? Well, what do we know? We know the car was off. We know this is clearly the power button based on how it's labeled and where it's located. And most importantly, when I pressed it, we heard kind of a happy confirmation-y sound. So did the car turn on? Actually, it didn't. To turn this car on, you have to press the brake pedal while pressing the on button. The car doesn't do a great job of helping us across that gulf of execution. There's no indicator that you're doing it wrong until you've actually already done it wrong. But the car does give us a short gulf of evaluation. If you do it incorrectly, an alert pops up on the dashboard letting you know you need to press the brake pedal and then press the on button. The output presented is easy to interpret, and it's presented in the context of when you need to know that information, so you kind of understand that it's a response to what you just did. So here we have some trouble with the gulf of execution, but the gulf of evaluation is still pretty short. So now that I see this message, I press down the brake pedal, press the on button, and now the car is on. So now that we've seen the way this feedback cycle currently works, let's talk about improving it. How might we make this feedback cycle even better? How might we narrow the gulf of execution and the gulf of evaluation? So here are a few ideas that I had. We know that the screen can show an alert when you try to turn the car on without pressing the brake pedal down. Why not show that alert as soon as the driver gets in the car every time? That doesn't widen the gulf of execution for an expert user, but it does narrow it for a novice user, because even a novice can see that alert the first time they get in the car. But what still throws me off to this day is the sound the car makes when you try and turn it on. Watch. Did the car turn on? No, it didn't that time. Now it turned on. So it plays the same sound initially when you press the button, and then plays a different follow-up sound to confirm that the car actually turned on. I know why they do this, that one sound just confirms that you pressed the button successfully while the other sound confirms that the car turned on. But for me, I would just as soon have two different sounds confirm whether or not you just pressed the button or whether the car turned on. That way, just the presence of a sound confirms the fact that the button was pressed, and the nature of the sound confirms the effect of that press. I asked you earlier to pick an area of HCI in which you're interested and reflect on it as you go through this course. Depending on the area you selected, feedback cycles can play a huge number of different roles. In healthcare, for example, feedback cycles are critical to helping patients manage their symptoms, and that relies on the results of certain tests being easy to interpret and evaluate. Feedback cycles are also present in some of the bigger challenges for gesture-based interactions. It can be difficult to get feedback on how the system interpreted a certain gesture and why it interpreted it that way. Compare that to touch, where it's generally very easy to understand where you touched the screen. So think for a moment about how feedback cycles affect the area you chose to keep in mind. Lately, I've encountered another interesting example of feedback cycles in action. You may have actually seen this before as well. They're the new credit card readers. My wife sells arts and crafts at local events, and so she has these square readers that can scan credit cards on her phone. One version lets you swipe, and the new version lets you insert the card. So let's check this out real quick. With the swipe version, you just insert the card and pull it through, just like a traditional card reader. The problem is there's typically no feedback on whether you're swiping correctly, and what's more is you can be wrong in both directions. You can be both too fast or too slow. So you may have had a time when you were trying to swipe a credit card on some kind of reader, and you kept doing it more and more slowly and deliberately, thinking that the problem was that you had done it too fast originally. And then you discover that you've actually been going too slowly all along, and your slowing down was actually counterproductive. There's no feedback here, and the space of acceptable input is bounded on both sides. You have to go above one speed and below another speed. But now credit card readers are moving to this model where you just insert the card. You try at least. In terms of feedback cycles, in what ways is this actually better? First, in terms of the gulf of execution, the insertion method is actually physically easier to do. While you can be both too fast and too slow with the sliding method, you can't push it too far in with the insertion method, so you know if there's an error, it's because the card isn't far enough into the reader. And second, there's rich feedback with the insertion method. It doesn't even have to come from the screen telling you that you didn't do it correctly. You feel the card stop when it's far enough into the reader. You have immediate physical feedback on whether you're putting it in the right place and whether you've actually put it far enough in, rather than delayed feedback asking you to try again after some kind of waiting period. So, using the insertion method is significantly easier. However, the insertion method introduces a new problem. With the sliding method, I never had to actually physically let go of my card, so there was little chance of me walking away without it. With the insertion method, I insert the card and I wait. I'm not used to having to remember to retrieve my card from the card reader. Now, this isn't quite as big a deal with these new portable readers, but for the mounted ones you see in stores, it can be far more problematic. So how can we build some feedback into the system to make sure people remember their cards when they walk away? There are a few things we could do here. We might build some kind of buzzer into the card reader to let the customer know when they can take their card out. That would make sure that they don't leave without it. ATM machines often do this actually. They'll ring a buzzer until the card and the cash are removed. But that's noisy and potentially irritating. It would mess with the ambiance of a restaurant or something like that. We could do something super complicated, like pair the credit card with a smartphone and ring the phone when it gets too far away from the credit card. But that requires adding some new technology to every single credit card, which could be a pretty big expense. So what about something simpler? Why not force a customer to remove the credit card in order to get their receipt and their goods? Unless they're going to walk away without what they came to buy, that'll ensure that they remember their card. Now notice one last thing about this example. We've been discussing how to make the process of sliding or swiping a credit card easier. What's wrong with that question? The problem is that we're not focused on the right task. Our task shouldn't be to swipe a credit card or insert a credit card or anything like that. Our task should be how to most easily pay for purchases. And possibly the easiest way to do that would be to design a system that lets you just tap your phone against the reader. This reader actually does that. That way, we can use the thing that people have on them at all times. Now, maybe that isn't the best option for various other reasons, but the important thing is we need to focus on what we're really trying to accomplish, not just how we've done it in the past. We can make incremental improvements to sliding or swiping or inserting a credit card all we want, but we should always keep our eyes on the underlying task that the user needs to accomplish. Today we've talked about arguably the most fundamental concept of human-computer interaction, feedback cycles. We describe feedback cycles for our purposes as the exchange of input and output between a user and a system to accomplish some goal. We discuss feedback cycles' incredible ubiquity in other fields and discussions. We talked about goals of execution, the distance between knowing what they want to accomplish and actually executing the steps necessary to accomplish it. We talked about goals of evaluation, the distance between making some change in the system and evaluating whether or not the goal was accomplished. We introduced the 7 questions we need to ask ourselves to bridge those goals. Now that we understand these goals, our next goal is to understand methods for crossing them.